There is something about the sky that should bother you. Not the stars themselves, but what they are actually telling you when you look at them. Every point of light you have ever seen was a message sent a long time ago, from a place that may no longer look the way it looked when the light left it. You are not looking at the universe as it is. You are looking at the universe as it was, layered on top of itself. 1,000 different pasts arriving in the same instant, all pretending to be a single present moment. That alone is strange enough, but it is not the part that should unsettle you most. The part that should unsettle you is this: the space between you and that light is not standing still. It is stretching. Right now, while you sit somewhere warm, reading or listening to this, the fabric that light is traveling through is quietly expanding, carrying distant galaxies away from each other in a way that has little to do with anything moving through space and almost everything to do with space itself growing. And if that stretching does not stop, if it does not slow down, if it keeps accelerating the way the evidence says it is accelerating, then there is a version of the future in which distance itself becomes a kind of violence. A future in which space pulls apart everything it once held together, not with an explosion, but with a silence so complete that it has a name among physicists who study it seriously. They call it the end of everything meaningful happening at all. Here is the paradox at the center of this. The universe looks, on the largest scales we can observe, remarkably calm. Galaxies drift, stars burn. Time passes in what feels like an orderly, almost gentle way. And yet underneath that calm is an acceleration, a force pushing space outward faster and faster, and no one fully agrees on what that force actually is. We have given it a name: dark energy. But a name is not an explanation. It is closer to a placeholder for our ignorance, a way of admitting that roughly 70% of the total energy content of the universe is doing something we can measure but cannot yet explain. So the promise of this film is not a comfortable one. We are going to follow the expansion of the universe to its logical end, layer by layer. And by the end, you will understand why some physicists believe the fate of everything is not fire and not collapse, but distance. An ending written not in destruction, but in the slow, patient stretching of the space between all things. If you are new here, welcome and settle in, because today we are going to follow this question as far as it can take us, past comfortable answers, into the parts of physics where certainty runs out and something stranger begins. Start with something small, something you already understand in your body before you understand it in your mind. Stand outside on a clear night, far from any city light, and look up. What you feel first is not scientific. It is something closer to smallness. A sense that you are standing at the bottom of something enormous, and that the enormity does not care whether you are there to notice it. That feeling is not irrational. It is your nervous system correctly registering scale, even before your intellect can process what scale actually means out there. The stars you see are not just far away in the way a distant mountain is far away. They are far away in a way that involves time itself, because light takes time to travel, and so distance and history become the same measurement. Now, take that feeling and multiply it by something almost impossible to hold in the mind. The light from the nearest large galaxy beyond our own took millions of years to reach you. The light from the most distant galaxies we can detect left its source before the Earth itself existed. When you look at the deepest images astronomers have captured, you are not looking at galaxies as they are today. Many of them are gone, changed beyond recognition, or transformed into something else entirely. You are looking at ghosts, except the ghosts are made of light, and the haunting goes only one direction, forward through space, until it happens to intersect with your eye on this particular night, on this particular unremarkable planet. But this is still just the surface, because so far, all we have described is old light arriving late. The truly disturbing part is not that the universe is big, it is that the bigness itself is increasing, and increasing in a way that breaks the ordinary intuition of movement. Think for a moment about how you normally understand distance. A road between two towns does not get longer while you drive it. A room does not expand while you sit inside it. Distance, in ordinary human experience, is a fixed quantity, a backdrop against which things move, but never a thing that moves on its own. Everything about how you navigate the world, how you judge how long a walk will take, how you estimate how close something is, depends on this quiet assumption that space itself holds still, and only the things inside it go anywhere. This assumption has never once failed you in your entire life. It has never needed to be questioned, because at human scale, over human time spans, it is, for all practical purposes, true. But it is not true at the scale of the universe. And this is the first place where the ordinary confidence you bring into this subject has to be set aside, because the largest patterns in the cosmos do not answer to the same rules that govern a room, a road, or a walk to work. Here is where we need the actual mechanism, the scientific explanation underneath the feeling of scale. When astronomers observe distant galaxies, they notice something that at first sounds simple. The light from those galaxies is shifted toward the red end of the spectrum, a phenomenon called redshift. In ordinary experience, redshift would suggest that an object is moving away from you, the same way a passing ambulance siren drops in pitch as it recedes. And for a long time, that was the assumed picture. Distant galaxies flying away from us through space, like debris from an explosion. But that picture turns out to be subtly wrong, and the correction is one of the strangest ideas in modern cosmology. The galaxies are not for the most part, moving through space away from us. Space itself is expanding, and the galaxies are essentially stationary relative to the fabric they sit in, being carried apart the way two dots drawn on the surface of a balloon are carried apart as the balloon inflates. Neither dot moves toward the other's location. The surface between them simply grows. This is the first place where intuition begins to fail, because we're used to thinking of expansion as something happening inside space, an explosion pushing matter outward into an empty void. But this is expansion of space itself, with no outside for it to expand into, and no explosion at any single point, because every point in the universe is, in a sense, the location where the expansion is happening. It is worth sitting with how counterintuitive this actually is. Ask yourself where the center of the expansion is, the point everything is rushing away from. And the honest answer is that there isn't one, not in the way the question expects. An observer in any galaxy, anywhere in the universe, would see every other galaxy receding from them in exactly the same pattern you see from here. This does not mean you are at the center of the universe. It means the universe, if it has a shape at all on the scales we can measure, has no privileged center and no privileged edge. The error in the intuition is assuming that an expansion needs a middle to expand from, the way ripples need a stone dropped into water. The universe's expansion is not like a stone dropped into water. It is more like the water itself quietly becoming more water everywhere, all at once, with no single point of origin anyone standing inside it could ever locate. This is the part that quietly changes everything. If space itself can stretch, then distance is not a fixed backdrop against which things happen. Distance is a variable, something that can grow on its own, independent of anything moving through it. And once you accept that, you have to accept a stranger consequence. Two galaxies can end up moving apart from each other faster than the speed of light. Not because anything is traveling that fast, but because the space between them is growing fast enough that the total separation increases at a rate light itself cannot keep up with. This does not violate relativity, because nothing is moving through space faster than light. But it does mean that there are galaxies out there right now whose light will never reach us, no matter how long we wait, because the space between them and us is growing faster than light can cross it. Consider what that means at galactic and supergalactic scales. Galaxy clusters that are gravitationally bound to each other, held together tightly enough that the local expansion cannot pull them apart, will likely remain together indefinitely. Islands of structure in an increasingly empty sea. But everything outside those gravitationally bound islands, everything not tightly held, will be carried away, first slowly, then faster, then at a rate that eventually outpaces the speed at which light can cross the growing gap. If the acceleration continues at its current trajectory, there is a future, unimaginably distant, but not infinite, in which every galaxy outside our own gravitationally bound cluster becomes invisible to any observer inside it, redshifted into darkness, carried beyond the cosmic horizon forever. Picture what that would actually look like from the inside, not as an abstraction, but as an experience unfolding across a span of time so vast that human history would register as less than an instant within it. Over tens of billions of years, the most distant galaxies would first dim, their light stretched into wavelengths too long to detect, fading the way an ember fades once the last heat leaves it. Then, nearer galaxies would follow, one by one, crossing the same invisible threshold, until eventually, an observer looking outward from within a single surviving cluster would see nothing beyond it at all. Not because those other galaxies had been destroyed, but because the space between here and there had grown too fast for their light ever to complete the journey. A future intelligence, evolving that far ahead, might look at the sky and reasonably conclude that its own cluster was the entire universe, with no way of knowing that an unimaginably larger cosmos once surrounded it, now separated by a gulf no signal could ever cross again. Now, widen the frame further, because a strange mechanism at galactic scale becomes something almost incomprehensible at cosmic scale. In the early universe, gravity was winning. Matter was dense enough and close enough together that its own gravitational pull was slowing the expansion down, the same way you would expect thrown debris to slow under gravity's pull. Cosmologists assumed for most of the 20th century that the only real question was how much the expansion would slow and whether gravity would eventually win completely, pulling everything back into a final collapse. Then, in the late 1990s, observations of distant exploding stars, a particular type of supernova whose brightness can be used as a reliable cosmic ruler, revealed something that did not fit the expected picture at all. The expansion was not slowing down. It was speeding up. Something was pushing space apart, harder than gravity was pulling it together. And that something was not previously accounted for in any existing model. This is the discovery that produced the term dark energy. Not because we understood what the energy was, but because we needed a label for a measurable effect with no confirmed underlying cause. But to understand why this discovery landed as such a shock, you have to understand what almost every physicist expected to find instead. For decades, the central question in cosmology was not whether the expansion would slow, but by how much, and whether that slowing would eventually reverse into collapse. Entire research careers were built on refining measurements of that expected deceleration. When the supernova data came back showing acceleration instead, the result was, for a period, met with genuine disbelief. Teams double-checking their instruments and their statistics before accepting what the measurements were telling them. This is the part that rarely gets said plainly. The discovery of dark energy was not a triumphant confirmation of an existing theory. It was an admission that something fundamental about the universe was and remains unexplained. But here is the anomaly, the place where the story stops being clean. We do not actually know what dark energy is. We know how it behaves, in the sense that we can describe its effects mathematically and confirm those effects through multiple independent lines of observation. But behavior is not the same as identity. Some physicists model it as a property of space itself, a constant energy density inherent to the vacuum, sometimes called the cosmological constant, an idea that traces back to a term Einstein originally introduced and later reportedly regretted, before observations decades later suggested he may have been onto something after all. Other physicists propose that dark energy is not constant at all, but a dynamic field that changes over time, sometimes called quintessence, which would imply the acceleration itself could shift, slow, or even reverse under conditions we do not yet understand. This is the detail that changes everything about how confidently we can describe the future. If dark energy is a true constant, unchanging in strength forever, then the accelerating expansion continues indefinitely, and the long-term fate of the universe is essentially locked in, an ever emptier cosmos, stretching toward what physicists call heat death, a state of maximum entropy in which no more useful energy differences remain to do anything, not to move, not to think, not to burn. But if dark energy changes over time, the future becomes far less certain. Some models suggest it could weaken enough to allow gravity to reassert dominance, pulling everything back into contraction. Other, more exotic models suggest the opposite, that dark energy could strengthen so dramatically that expansion accelerates without limit, eventually tearing apart not just galaxies, but stars, planets, atoms, and finally, the fundamental structure of space-time itself, an outcome given the almost theatrically bleak name, the Big Rip. And here, the story takes a turn that has only sharpened in the last few years. For a long time, the cosmological constant, dark energy as a fixed and unchanging property of space, was the simplest assumption, and the evidence was consistent with it. But recent measurements from large surveys mapping the positions of millions of galaxies across cosmic time have produced something unexpected. Hints, not yet proof, that dark energy may not be constant after all, that its strength may have been subtly changing over the history of the universe. The signal is real enough to take seriously, and at the same time weak enough that reasonable physicists still disagree about whether it will hold up as more data arrives. Depending on which sets of observations are combined, the evidence ranges from mildly suggestive to moderately compelling, but none of it yet reaches the threshold that cosmologists would require before declaring the cosmological constant genuinely overthrown. So, we do not currently have enough evidence to say with certainty which of these futures is correct. This is not a settled question. It is one of the most actively contested frontiers in all of physics right now, dependent on extremely precise measurements of how the rate of expansion has changed and continues to change over billions of years. Measurements that are still being refined and still being argued over. What we can say is that all currently viable models involve the same underlying, unsettling fact. The space between things is not a passive stage. It is an active participant in the story of how everything ends. This is where we need to go one level deeper, into the physics that makes any of this possible in the first place. Because so far, we have described what is happening, without fully explaining why space is even allowed to behave this way. The answer requires general relativity, the framework in which gravity is not a force pulling objects together in the way a rope pulls, but a curvature of space-time itself, caused by the presence of mass and energy. Under this framework, space-time is not a fixed container. It is a dynamic structure that responds to what fills it, stretching, curving, and evolving according to precise mathematical relationships described by Einstein's field equations. Intuition would suggest that empty space should simply be nothing, a kind of blank absence with no properties of its own. But general relativity, combined with quantum field theory, suggests something stranger. Even a region containing no particles at all still has properties, including potentially an intrinsic energy density belonging to the vacuum itself. It is this vacuum energy, or something behaving very much like it, that current models point to as the source of the accelerating expansion. In other words, nothingness itself may not be empty in the way we assume. It may have a kind of pressure, an outward tension, built into the basic structure of space. This is the layer where the mistake in ordinary thinking becomes clear. We imagine that if you remove everything, matter, radiation, light, motion, you are left with true nothing, a blank stage with no properties and no behavior. But the mathematics of modern physics suggests otherwise. The vacuum is not passive. It has structure. It has energy. And that energy appears to be doing something to the geometry of the universe on the largest scales. Something that behaves almost like a form of negative pressure, pushing space outward rather than pulling it together. The intuition fails because we built it entirely from experience with objects, things that need a push from something else in order to move. Space does not need to be pushed by anything external. Its expansion appears to emerge from its own internal properties, a self-sustaining process with no external engine required. Now, the deepest layer, the place where even the most confident physicists become careful with their language. If the accelerating expansion continues indefinitely, the long-term future of the universe is often described using the concept of entropy, a measure, in simple terms, of how evenly energy has spread out and how much of it remains available to do useful work. The second law of thermodynamics states that in a closed system, entropy tends to increase over time, meaning energy naturally spreads from concentrated, useful forms into diffuse, less useful forms. Applied to the entire universe, this suggests a final state in which all energy has spread out as evenly as possible. All temperature differences have vanished, and no further work, in the physical sense, can be done. No stars can ignite. No structures can form. No process of any kind, including anything resembling thought, memory, or motion, can continue. This state is called heat death, and under most current models, it is the most likely long-term outcome if dark energy remains constant. But here is where the ground beneath even that conclusion becomes uncertain. We do not fully understand what dark energy is. We do not fully understand whether it can change over time. And we do not fully understand the ultimate quantum nature of space-time itself at the smallest scales, where general relativity and quantum mechanics have not yet been successfully unified into a single consistent theory. Some highly speculative frameworks, still very much on the frontier of research and not established fact, propose that a true vacuum state may not be perfectly stable, that space-time itself could, in principle, transition into a lower energy configuration, a process sometimes called vacuum decay, which would not simply end our universe, but replace its fundamental physical laws with different ones, expanding outward at the speed of light with no warning of any kind. This remains speculative, a hypothesis explored seriously by physicists, but nowhere close to confirmed, and it sits at the edge between physics and the unknown, precisely because the underlying question, what is empty space actually made of, remains open. So the question the entire film has been circling stops being a question about galaxies or light or even the fate of stars. It becomes a question about whether the universe, at its most fundamental level, is a stable structure at all, or a temporary configuration sitting in a valley of possibility that may not be the lowest valley available. Return now to the beginning, to the feeling of standing outside on a clear night, small beneath something enormous. That feeling was correct, but it was incomplete, because the enormity above you is not simply large. It is actively growing, carrying itself apart, and in doing so, writing an ending into the structure of reality long before that ending arrives. The paradox from the opening was this: everything looks calm, and yet everything is accelerating apart. That paradox does not resolve by the end of this film. It deepens, because now you understand that the calm is temporary, borrowed against a future in which the sky itself will, over spans of time larger than the current age of the universe, many times over, go dark, galaxy by galaxy, as each one crosses beyond the horizon that light can still cross to reach us. And yet, within that unimaginably long stretch of time, something else remains true, something almost impossible to reconcile with how bleak the physics sounds when described plainly. For as long as stars exist, for as long as energy differences remain anywhere in the universe, structure, complexity, and perhaps something resembling awareness remain possible. The end of everything, if it comes the way the current evidence suggests, arrives not suddenly, but so gradually that entire civilizations, if they exist, would have unfathomable spans of time to exist, to wonder, and to ask exactly the question you are asking right now, before the answer finally, quietly, arrives. The universe does not appear to be trying to stay still. It appears to be carrying forward a kind of motion that began before any star had a name, before any observer existed to notice it. Expanding not because something is pushing it from outside, but because expansion may simply be one of the deepest properties of existing at all. Whether that motion ends in silence, in tearing, or in something we do not yet have the physics to describe, remains, for now, one of the largest open questions asked by anyone who has ever looked up and felt small beneath something that refuses to stop moving. Consider one last time the image this film began with. You standing beneath a sky full of arriving light, feeling small in a way that turned out to be entirely justified, though not for the reason you first assumed. You were not small merely because the universe is large. You were small because you exist inside a single brief slice of a process that started long before you and will continue long after. A process that does not pause to acknowledge the presence of anyone watching it unfold. And yet, within that brief slice, something remarkable happened. The light reached you. A question formed. A mind capable of understanding, even partially, the shape of its own ending came into being for exactly long enough to ask what that ending means. That may be the strangest fact in this entire story. Stranger even than expanding space or invisible energy, or the possibility of a rip in the fabric of existence. Somewhere in a universe that appears by every available measurement to be drifting towards silence, something arose that could notice the silence coming and choose for a while to look up anyway.